This is Dr. Wood with Citadel Civil Engineering, and this is CIVL202 Statics. In this lecture, we're going to introduce the idea of a moment of inertia from Learning Objective 6. Just as a reminder, this is the best day to learn statics because we're going to be using statics a lot going forward. And in fact, I would add that when we look at moment of inertia, which is a little bit of an add-on to what statics is, it's using moment of inertia that will allow us to do many of the things that we intend to do in mechanics of materials when we look at deflections and stress distributions in beams. And so with that in mind, I'd like to give you a problem that looks a little bit convoluted, but actually relates very well to many problems that we see in fluid dynamics, hydrostatic pressure, and in mechanics of materials. So what we have here is a linearly increasing pressure. And if we think about what we've been given, we're told that that pressure is going to increase with a linear slope. So I've got an m times x. So this would be like mx plus b, where this is my slope, and x is my position along that x-axis there. So as it increases, that pressure is gonna go up. And so what we're trying to find is a calculation of the moment, the moment around the, in that case, it's the y-axis, the moment about the y-axis. Okay, so our procedure for working a problem like this, so this is going back a little bit, looking at resultant moments. We would want to just be able to identify our forces and perpendicular distances, right? And then from there, we can say that our moment is equal to R cross F, or F times D perpendicular. Well, if we think about this as we look at it, I'm going to do it down here, save some whiteboard space. If we think about this as we look at this, I can kind of blow this out a little bit so you can see more what's going on the whiteboard. Actually, I want to look here. We've got a differential area that's acting across here that would give us this differential portion of the force. So we're going to be doing some integrating. And so if I think about that differential portion of the force, it's going to be equal to that pressure times the differential area. So the pressure times the differential area, right? P times A is equal to our force. And so P is mx. And so that's going to be multiplied by the differential area, like so. And our perpendicular distance, D perpendicular, is going to be equal to just the x-axis. So that's going to be the distance along this x-axis through here. So as I look at that, make my math a little bit bigger, I can calculate my moment as just the perpendicular distance times the differential force. So my moment is going to be equal to the integral of D perpendicular dF, which is equal to the integral of x times mx, where m is the slope, dA. We agree with this? I hope we do. Okay, so if m is the slope, it's a constant. And so what we'll find is that the moment is equal to m, which can be pulled outside the integration, dx squared dA. Now, hopefully you remember seeing something that looked like this, where it was the integral of x dA. We called that the first moment of area, and we used it to calculate a centroid. Now that we have two x's, we're going to call this the second moment of area, or the area of inertia. Okay, and it gets used in problems that take this form of a linear increasing pressure. And then, so then your mechanics of materials or your fluids is going to explore what that slope is. But we're going to master today in statics this idea of calculating the moment of inertia. This is area moment of inertia. So we want to master measuring this area moment of inertia or calculating it for a given shape today, and that ends up being a area moment of inertia. That ends up being a mathematical function. And so if we look here at our slides, we can see that we got some math going on. So just as a reminder, the first area or the first moment of inertia we used to calculate the centroid, where we had 1x dA, and we integrated that. Well, we're going to now expand that to the area moment of inertia. And it matters which axis we're working around, but fundamentally this is just a geometric property. So Iy, the area moment of inertia about the y-axis, is going to be equal to the integral x squared dA. So there's a mismatch here, because if we think about the y-axis, the perpendicular distance to the y-axis is x, right? So x squared dA, like so, and Ix, so the moment of inertia about the x-axis, is equal to the integral of y squared dA. And so in each case, we have the perpendicular distance back to the axis squared, because remember, area moment of inertia is the second moment of area. So we have two perpendicular distances times the differential area. You can find this in your FE reference handbook. FE reference handbook on pages 35 and 72. Okay, so this is stuff that's in your FE reference handbook. You don't have to remember it. Now, just like over here we calculated the area moment of inertia and the centroid, we can now calculate the second area moment of inertia and the radius of gyration. So radius of gyration is a bit like the centroid, and again, it's going to be radius of gyration. The radius of gyration is going to have, let's look at units, right? Up here, we got distance squared times area, so it's going to be like inches to the fourth or meters to the fourth, kind of a weird unit. Radius of gyration is just going to have a distance, right? So the way that's going to look is that Ry is equal to the square root of Iy over A. Now this is actually going to be an x-axis direction, right? And Rx is equal to the square root of Ix divided by A. And what we're doing here is we're normalizing with respect to the area. And so the way you can think about this is that the radius of gyration is the distance from the center of gravity of the body, out to, or wherever the axis of rotation is, so either Ix or Iy, out to the center of mass, more or less, of where the material is as it would rotate. So moment of inertia, radius of gyration, those are thinking about rotational components. And this is on page 73 of your FE reference handbook. Page 73. Okay, so we have area moment of inertia. We have radius of gyration. If we're given the radius of gyration, which this is often very helpful for someone to just come along and give us the radius of gyration, we can calculate the area moment of inertia just by doing Ry squared times the total area, or Rx squared times the total area. So all we have to do is take that radius of gyration, square it, and multiply it times the area, and now all of a sudden we're going to have the answer. So that's kind of what's going on there. Now, there's one more concept we use that's related to torsion, so twist. And this is called the polar moment of inertia. Okay, and this looks at, you can think of this almost as like Iz, so the rotation about the z-axis for an area like this. And so Iz, we use the symbol J to indicate polar moment of inertia, and it's going to be the integral of r squared dA, where r squared is the radial distance, right? But r, we can calculate r as the square root of x squared plus y squared square rooted, right? So yeah, r squared equals x squared plus y squared, which if we do some substitution, we'll find that this polar moment of inertia is just equal to ix plus iy. And so if you've been able to calculate your ix and iy, you can just add them up to find the polar moment of inertia for twist. And again, this is in your FE reference handbook on page 72. All right, so we use Pythagorean theorem there, and we're able to get the polar moment of inertia. Now, when we were looking at centroids, we use the idea of a center of gravity, and then we move to center of mass, and then a volume centroid, and then from a volume centroid to an area centroid by assuming constant either gravitational field, density, or thickness. Well, it turns out you can do the same thing, and we can take this area moment of inertia, and we can multiply it by a constant thickness and then a constant density, and we'll get the mass moment of inertia. And this is going to be useful in dynamics, the mass moment of inertia. And so that's going to be equal to I is equal to r squared dm, where we have that differential mass. We got that differential mass by taking our differential area and multiplying it by a constant thickness and a constant density. If we don't want to do that, we can always do radius of gyration times the total mass to get the mass moment of inertia. And so this is the classic problem from dynamics if we think about like the figure skater problem, right? So when you think about the figure skater, a large moment of inertia means that you're going to have low angular acceleration. A high moment of inertia means you're going to have high angular acceleration. It's also related to angular momentum, so how quickly we're spinning, right? So I times omega is going to give us our angular momentum. And if our angular momentum, if our mass is out, so when the figure skater has their arms spread out and their legs spread out and they're spinning, they will spin slowly because they have one angular momentum, I times their omega, so their angular velocity, how quickly they're spinning, it's going to be equal to the angular momentum. But if they bring in that I, they bring in their arms, and so now their radius of gyration goes from the center of mass being kind of out here to very close to their body, right? They will spin much faster because they're going to maintain that constant angular momentum, but I has gone down, so their omega, their angular velocity, has to go up. And so maybe this is a concept that you're actually familiar with and you can think of from a mass point of view. And in fact, next time we'll look at a shape like this, right? And we can see that if we pick an axis that looks something like this, right? So my axis is vertical off the screwdriver. All the mass is very close to this axis, and so it spins pretty easily. But if I look at this axis, the mass is spread out. It has a much greater radius of gyration, and so it's going to spin more slowly, if y'all see that. So that's the idea. But we're thinking about mass in that case. We'll actually get to calculate that in a couple of lectures. So that means that we'll have a radius of gyration for mass as well. The radius of gyration for mass being Rm is equal to the square root of I divided by the total mass. And that's all pretty good. Now, the question that we really want to be able to answer is how do we actually solve this right here, right? How do we solve for the area moment of inertia? And so I'm going to clear the board a little bit, and we're actually going to do a solution of this particular problem. And it's going to look a whole lot like how we calculated the centroid location for a body. Okay. So give myself a little bit of board space. And so when we think about this, remember when we did the centroid location, your textbook has a couple of different ways that you can calculate this area moment of inertia or the location of the centroid doing single integration, where basically you find the area of a slice of the body and then you integrate along the length. But I find that it is far more robust for us to do double integration. As much as that may not be as mathematically fun, it will certainly get get the job done. And so if we think about some arbitrary shape, I like to do something like this. That look okay? There's a nice arbitrary shape. Okay. And we want to find the moment of inertia about the x or the y-axis. The way that we're going to do this, our procedure, so this is for area, moment of inertia. It's going to be very much similar to the area moment or the area centroid location that we did. So our first step is going to be to identify a differential area. Now, if you're doing what our author does in his textbook, he's going to go through and cut out a little sliver of the thing and figure out what its area is. But if I'm doing double integration, I can just say, here's my differential area, and it is a differential unit y tall and a differential unit x wide. And so dA is equal to dy dx. The next thing we need to do is figure out the centroid for that differential area. And so our author would look at that sliver and try to figure out where the middle is. But if I'm doing double integration, all I have to say is that I can find the centroid on this, this value x here, right? And it's going to be some distance y away from the x-axis. So I find my centroid, x and y, like so. And then just like we did for our centroid calculations, we need to find our limits, a, b, f1x, and f2x. And so what I'm going to do is I'm going to look here and I'm going to say, well, my minimum x value, I'm going to call that point A. And my maximum x value, I'm going to call point B. My upper bound function, so this is a y value, is going to be f2x. So for each given x value, I get the y value. And my lower bound function, I hope you can hear the marker squeak. It's a beautiful sound. Would be f1 as a function of x. So for each value of x, I get a y value there. And then finally, I will set up my double integration. And so I'll integrate. I'll integrate. And so the way I want to integrate this is IY is going to be from the lower bound x to the upper bound x, lower function, which is y, to the upper function, which is y, and then IY uses the x squared. So I'm going to have x squared dy dx. And we'll remember, or at least be reminded, that if we're doing double integration, we integrate the inside component, so from the integral to the first differential unit first, and then we'll do the outside, like so. And I got that x squared in there because I'm doing moment of inertia. Ix is going to be the integral from a to b, integral f1x to f2x, y squared, because remember y is the perpendicular distance back to the x-axis, dy dx, with the same, integrate the inside part first, and then integrate the outside part. And so that's it. Now, that's very mathy. I agree, right? Very mathy. Very much a thing that's going to take us some effort to work out. But that will allow us to calculate the area moment of inertia. Once we know that, we can also calculate the total area, and we could solve for the radius of gyration if we wanted to. If we've solved for both area moments of inertia, we can add them together to get the polar moment of inertia. And so that's how we can do this for area. So this is going to be the main thing I want you to be able to do for at least one of your homework problems. I won't put any double integration on the exam. We'll work a double integration problem like this for a rectangle and for a triangle in the Zoom class, and then we'll go from there. All right, look forward to seeing you in class.